Generalizing the Ehrenfest theorem. Last question we worked with the generalized uncertainty principle, so naturally we run into the generalized Ehrenfest theorem on our way to understanding the uncertainty in energy and time, because the rate of change of time requires us to take the derivative of expectation values of the operators or observables. So with the time derivatives, Ehrenfest theorem of course comes in. So we wish to, in this question, apply equation 3.73, which is the generalized statement, to the following special cases, where we have the observable 1, observable h, or energy, the observable of position, and the observable of momentum. In each case, comment on the results with the particular reference to equations 1.27, 1.33, 3.8, and of course the conservation of energy, which were the remarks after 2.11. So, it might help for us to define what this equation actually is. And that's what we see here, the generalized Ehrenfest theorem. Now, note, of course, that this is not really named. This is what Griffiths and I believe Darrell agreed on. So nonetheless, the statement reads as the time derivative of the expectation value of the observable is equal to I over h bar with the expectation value of the commutator bracket with the energy, of course, and the observable of interest. And then, to tag along, you have the time derivative of the operator in the expectation. But they do make it a point to note here that in footnote 24, operators that depend explicitly on time are quite rare, and they are almost always zero. So for this exercise, we're going to assume that that last expectation value is zero, so let's be aware of that. And what we could state about this relationship in general is that, in particular, if the operator Q commutes with the operator H, or the energy operator, Hamiltonian operator, then we say that the expectation value of Q is constant. And in this sense, Q is a conserved quantity. Let's see how these apply with the examples given. In part A, we want the observable of just a constant, which is Q equals 1. Okay, now easy enough. You plug that in, you see the green matches everything. Not too big of a deal. What we can observe though is that here this commutator bracket and the time derivative are going to go to 0 each. For the bracket, we see that we just use the constant rule. If I have a constant, regardless of what order it is, the bracket evaluates to 0. No big deal. And so that's where we get the 0 in the purple there. And of course, with the red 0 from the time derivative, we get the whole right-hand side is 0. Cool, we expected that. We are still left with the comparison of the equation 1.27, which states that the time derivative of the integral expression here is equal to 0. Now let's recall that we had to have functions that were normalized. And so this means that psi star psi, which is the magnitude squared, is equal to 1. Okay, if that's the case, then this looks like the expectation value of 1, so we can see that these two equations are equivalent, and of course we see that this means that we have conservation of normalization, which is exactly what we hope to have for any time dependency due to the fact that the Schrödinger equation has a time-dependent partial derivative. Wonderful, we like that. So we're good there. Moving on to case B then. Let's see what we have. B, we want just the observable of energy itself, which of course, if we plug that in, we get H, H, H all across the board. Here we are making explicit reference to the fact that we are hoping that we are not time dependent in this Hamiltonian. We're not going to take cases like the harmonic oscillator. So with that in mind, this expectation bracket goes to 0, and we're still left with evaluating the H bracket here. But of course, since we know what our commutator relations, that if we have the same operator in the bracket, that evaluates to 0. So once again, we get another 0. We like that, all nice and summarized here. And so if we compare this to the remarks of 2.21, we have the conservation of energy restored, okay? And in fact, we can verify this mentally because we know that the summation here leads to a finite number, right? If I just sum up a bunch of numbers, right, that are all supposed to converge or be discrete, a discrete set of numbers, I know that that is another number. So the time derivative of a number is 0. So we again recover the conservation of energy equation. And it's remarkable to see the consistency built in, but it's nice to see how. All right, moving on then. So in part C then, we want for the observable of position. So plug it in. Boom, boom, boom. You see again, we make an explicit reference that this is not changing in time. The observable is just the variable itself. So we see that position wants to measure position. Cool, no big deal. Now the commutator bracket looks like something we've seen before. In particular, we saw this in equation, or not equation, but problem problem 3.15. Recap from there. We saw that the expectation of x with the Hamiltonian led to the IH bar P over M. However, we have the reverse case, which is okay because, if we have the opposite order, we can use the anti-symmetry property here. And what we can verify is that we could switch the order at the cost of a negative sign, which we do here. We have the negative sign. Let's also note that in the commutators, we could go ahead and in the expectation value, we can go ahead and factor out the constants and push them outside because we know they're both linear. And we get the negative 1i h bar over m all on the outside, leaving the absolute value, the expectation of p in the middle. Okay, so what we see here is that I and I go to negative 1, cancels with this negative. Then h bar and h bar cancel, leaving us with just p over m. Cool. If we go back to equation 1.3 from chapter 1, where we saw that momentum was equal to m d by dt of the expectation of x, Ehrenfest theorem in the case of momentum, we see that we recover the equation. Although not explicitly stated in the text itself, but rather a footnote in the homework, we saw that this was again, some authors like using the momentum and the expectation of momentum time derivative as the Ehrenfest theorem. So a little shaky on the actual generalization, but be aware they are still there. All right, moving on to our final part then. Here in part D, what we wish to show is for the operator observable of momentum, we wish to show the same thing here. Again, beware, not time dependent. We're trying to get rid of that just to highlight a point. And again, we see that if we want the expectation of P, we have to evaluate the commutator bracket here. But of course, we need to handle this with a little bit more care. And so we recall that we saw a problem like this in, I believe, question 3.14c. So if we recall that relationship, just like we did on the last part, here we see that we have this relationship going on. And so we need to recall that the Hamiltonian is composed of the momentum and the potential, no big deal. Use the linearity property, split them up. What we see here is that we have the p squared p plus v to the v and p. So we know that this goes to 0, of course, due to the same operator, meaning here that we would have p cubed minus p cubed, and that goes to 0. So again, abuse whatever we need to. As far as the relationships to verify and simplify, no big deal. So if that goes to 0, we're still left with trying to figure out what v and p are. And this is where the relationship from the question 3.14 part C comes in, because we found in that question that for any function that has a polynomial expansion, the Taylor series expansion, commuting with p, we get I h bar the derivative of f with respect to x. And so here, v and f are changing places, and that's how we end up with the IH bar partial v over partial x. So again, all these things are coming together. We like that. Pretty darn cool to see how it tidies up. H bar cancel. I goes to -1, and thus we see what the relation is here. And of course, if we compare this to the equation 1.38, which was the Ehrenfest theorem that we showed in a homework question, we show here that the time derivative had the negative inside, but of course, it being a constant can be pushed out because it's -1. So we bring it outside and we verify once again that we have exactly what we're looking for in the recovery of the equation. Pretty darn cool. Pretty darn cool. So thank you for watching, and until next time, stay curious. Happy learning.